In the last section, we looked at system of differential equations. So in this section, I want to look at an application of that, and that's the system of coupled mass springs. What do I mean by that is in the past, we looked at having a single mass attached to a spring, and then we would pull that mass, and then we would let it oscillate back and forth, and we would neglect friction of that surface. But here, we're going to look at, well, what happens if we have two masses? We'll just call that mass 1 and mass 2. And this spring has a spring constant of K1 and K2. So Newton's second law still applies when we sum our forces. That should still equal mass times acceleration. And we're going to neglect damping. So no air resistance, no surface friction here. The only forces that we're going to be looking at right now are the forces from the spring. I think there is an example in homework. I don't think I assigned this one, but we could say that there's an external force pushing over here, but I think we left that one off. So let's look at our equations here. So to do so, we need to define a measuring system. So we're going to describe the position of this mass as x and describe this one as y. So in this case, x is not horizontal and y vertical. They're both horizontal. They just have different positions. So here, this is the equilibrium position, so where x equals 0 for the first mass, and this is the equilibrium position for the second mass. We're going to call to the right positive. So if this mass is to the right over here, x is positive. If this mass is to the right here, then y is positive. So if we look at the first one, if we sum the forces, that should equal ma. So the mass 1 times the acceleration here, and we're going to call that acceleration x double prime, should equal the sum of the forces. So if right is positive, then this spring is pulling it to the right, so that's a positive force. This spring is pulling to the left, so that's a negative force. So let's describe this one first. So this spring has a spring force of minus K1 times x, because wherever this box is located, if I pull it to the right 1, then the x displacement is positive 1. If I pull the box over 2, when the box is over here 2 units, then this displacement is 2 units. So whatever the x position is, that's the displacement of this box. So that displacement times K1 is that force. And then this force, pulling it to the right, so that'd be plus K2. But then we need an expression for the displacement in that spring. So if they're both at equilibrium, then we're considering that 0 displacement. But if they move, notice they're both free to move. So, for example, if this one moved to the right 3 units, and this one moved to the right 1 unit, then what would the net displacement or the net stretch of that spring be? It would be 2 units, because if we move this, if we keep that still and move this to the right 3, then it has been stretched 3 units. But then if we move that to the right 1, then we've taken away one of those units of stretch. So the y position minus the x position, that's going to be how much that spring is stretched. So that's going to be our displacement for that one. So that's the forces exerted on that particular block. So now if we do that for the other one, on this block, then that mass times its acceleration, its position is given by y, so its acceleration is given by y double prime. equals, well, the only force pulling on that one, there's nothing pulling it to the right, so we have a force pulling it to the left, so negative K2, whatever the displacement of that spring is, which we demonstrated earlier as y minus x. So if we rearrange the first equation, if we get everything on one side, we have m1 x double prime. If we move that to the other side, we have a k1x. If we distribute there, we have a minus k2x. So when we add it, we have a plus k2. So both of those are coefficients of x. And then we have a k2y. When we move it to the other side, that'll be a minus k2y. And that's got everything on the left side of that equation. If we do the same thing for the second one, we have m2y double prime. We have minus k2y, so if we move that over, we'll have a plus k2y. We have minus times a negative, which is positive k2x. If we move it over, it'll be a minus k2x, and that equals 0. So now let's take a minute and let's convert these to just to denotation. So for this top one, for x, we have m1 times the second derivative of x. We have k1 plus k2 times x. So that's the operation on x. And then we have minus k2. That's the operation on y. Then for the next one, the operations on y, we have the second derivative, so d squared, and the second mass. And we also have y times k2. So those are the operations on y. And then the operations on x, it just gets multiplied by the opposite of k2. So having said this, let's go in and give some values. For this problem, let's suppose that m1 is 2 kilograms, m2 is 1 kilogram, k1 is 10/3 Newton per meter, k2 is 4 newtons per meter. So let's copy those and bring those down here. Not like that, but copy these. Well, I thought I copied it. Again, copy. Paste. Okay. So I didn't mean to get that. So we'll just cut that. Okay, so if we substitute these values in, then we have m1, so t d squared, not d double prime, but d squared, k1 plus k2. So if we add these together, that's 4, that's 10/3, so 4 is 12/3, 10 plus 12, that's 22/3. So that's the operations on x. K2 is 4, so that's the operation on y. And then for the second one, minus k2, so minus 4 is the operation on x. And then we have m2, so 1 d squared plus 4, that's the operation on y. All right, so we need to, this is a system of differential equations. It's linear, so we are able to eliminate a variable. So let's take the top one and the bottom one, and let's multiply by something and get rid of y. So if we take this coefficient and multiply times the top one, and that'll give us a minus 4 d squared plus 4 for the coefficient of y. And if we bring this coefficient and multiply times the bottom one, we're just going to multiply by a positive 4 because these signs are already backwards. So we're going to do this times that, and that's the messy part. So when we do this times that, let's go ahead and distribute that. That's 2d to the fourth. This times that. 2 times 4 is 8d squared. This times that, so 22 thirds d squared. 22 thirds times 4 would be 88 thirds. That's the operation on x. And then we have minus 4 d squared plus 4 as the operation on y. And anything times 0 on the right is 0. Out front, negative 4 times 4 is negative 16. That's our operation on x. And then we have plus 4 d squared plus 4 is our operation on y. And notice those cancel. So our y's are gone. We have no operation on y, or our operation is 0 times y, so our y's are gone. So if we combine like terms and simplify out front, we have 2d to the fourth. If we get a common denominator of 3 here, we'll have 24 plus 22, so that's 46 over 3. That's the coefficient of d squared. If we put this over 1, this would be 48 thirds. 88 minus 48 is 40 thirds. That's our operation on x. And to make the fractions go away, let's multiply both sides by 3. So we'd have 6d to the fourth plus 46d squared plus 40 as our operation on x, and that equals 0. If we want to, we can call that 6 times the fourth derivative of x plus 46 times the second derivative of x plus 40 times x equals 0. So our characteristic equation is 6r to the fourth plus 46r squared plus 40 equals 0, which that actually factors. That's not quadratic, but notice we have a constant, something that's a variable, and this is that squared. So we can factor it like a quadratic. We can call this 6r squared and this 1r squared. We can call this 40 and this 1. Notice that makes 40r squared and 6r squared. That's 46r squared. So if we set this one equal to 0, we'll subtract 1. R squared is negative 1, so r is plus or minus the square root of negative 1, which is I, or 1i. If we subtract 40 and divide by 6, r squared is negative 20 over 3. And we take the square root of both sides, then r is plus or minus I times the square root of 20 over 3. So we're assuming that x is going to be, because of our differential equation being homogeneous, that our x is going to have a solution like that. So x of t is c1. Notice there's not an a. This is, remember, a plus bi. A is 0, so there's not an e to the rt. So we have c1 cosine of bt plus c2 sine of bt. And then we go to our other a, bi. There's no a over here. B is 1. So we have a 3 cosine of 1t plus c4 sine of 1t. So that's our general solution for x. Now, based on initial values, we'll have to determine what c1 through c4 are, but that's our solution for x. We need to find a solution for y. So if we go back to our system of equations and we look at our let's see, where do I want to look? If we look here, then this top equation we could easily solve for y, which is this one. So let's see about copying it. Paste it down here. Let's plug our numbers back in. So our M1, this was 2d squared, and yeah, we'll go ahead and put it in this format first. 20 thirds, or not 20 thirds, but 10 thirds plus 4. That's our operation on x minus k2y, so minus 4y. If we move the 4y to the other side, that's just 4 times the function y. So we have 4y equals, so we move that to the other side and we flipped. So we have twice the second derivative of x, so 2x double prime. And then we have whatever this is times x. So that was our 22 thirds. That's our coefficient of x. So we can divide both sides by 4. So y is 1/2 of x double prime. If we divide this by 4, we're going to have a 4 on bottom, which reduces that 22, making 11 on top, 6 on bottom, x. So now that we know what x is, we can take the second derivative of x, take 1/2 of the second derivative, we can take our function of x, times it times 11, 6, combine those, and that'll give us y. So if we look at x here, x prime would be the first derivative of that. So the derivative of cosine is minus sine. But we have to use the chain rule, so we have our C1 out front, and we have to take the derivative of the inside. The derivative of the inside is square root of 20 over 3. Same thing here. The derivative of that one, the derivative of sine is cosine, times the derivative of the inside, and the derivative of the inside is root 20 over 3. Here, the derivative of cosine is minus sine, and the derivative of sine is cosine. So that's our first derivative, then our second derivative. And the derivative of sine is cosine times the derivative of the inside. So the derivative of the inside is another root 20 over 3, so we're going to have a root 20 over 3. We're going to have another root 20 over 3. Real quickly, root 20 over 3 times root 20 over 3 is root 20 over 3 squared, which is just 20 over 3. So when we take the derivative of that, we get the root 20 over 3. We get cosine of that times the derivative of the inside. That's where I mean the root 20 over 3. The derivative of the inside gives us another root 20 over 3. So that makes 20 over 3 out front times C1. Same thing here. When we take the derivative of that, we're going to have sine and minus sine root 20 over 3 times t times the derivative of the inside. The derivative of this inside is the square root of 20 over 3, so we're going to have 2 of those out front, which makes just 20 over 3. When we take the derivative of this, the derivative of sine is cosine. When we take the derivative of that, that's minus sine. So that's our second derivative. So we want half of that. So if we get half of our second derivative, this times 1/2, or this divided by 2, that'll give us 10/3 C1 of cosine minus 10/3 C2 of sine minus half of C3 cosine minus half of C4 sine. So that's 1/2 of x double prime. This was x, so if we multiply each one of those by 11/6, then we'll have 11/6x. So 11/6x double prime, not x double prime, but 11/6x is just 11/6 C1 cosine square root 20/3t, 11/6 C2 sine root 20/3, 11/6 C3 cosine, 11/6 C4 sine. So y is these two lines. Remember, y is 1/2 x double prime plus 11/6 x. So 1/2 x double prime plus 11/6 x. So y of t if we combine these, this is 26, this is 11/6. So 11 minus 20, that's minus 9/6, which is negative 3/2. Same thing here. When we combine those, we get minus 3/2 C2 sine. Here our common denominator is 6, so this is 3/6. So 11 minus 3 is 8. 11/6 minus 3/6, that's 8/6. 8/6, or 4/3. And these are the same, so plus 4/3 C3 sine t. Oops. So that's y. So again, let's paste x. That's not it. So there's x and there's y. So there are our solutions. We just don't have C1 through C4 yet. And this one is supposed to be a C4 here. So we have to have initial values in order to get C1 through C4. And we'll come back to that in a minute. So we looked at what we called our natural frequency when we were looking at one mass oscillating back and forth. Notice here we have two natural frequencies. We have a natural frequency due to these terms, and we have a natural frequency due to those terms. Same thing for x. So here we actually have two different natural frequencies. Depending on what our initial conditions are, that could make the C3s and C4 possibly go away, so we only have one frequency for y, one frequency for x. Could be that C1 and C2 are both 0, so our natural frequency might only be determined by this. But what may end up happening is we may end up having an oscillation that goes back and forth, but we have some intermediate oscillation in with it. So we might have two natural frequencies built into this oscillation. So let's look at our initial conditions and let's see what our coefficients are. And then if we have have time, an opportunity, we'll see about graphing these two different situations. So for our situation, it says we're going to hold the first mass still, and we're going to stretch the other one. So when our clock starts is when we release the second mass. So at the beginning, our x at time 0, our x position is 0. It's not moving. And at the beginning, its velocity is 0. It's being held still. So we're stretching this one over. So when time is 0, the amount of stretch that we're applying to that one is 1 meter. But we're not pushing it once we release it. At the moment we release it, it's going to be setting still. It's going to be under a different amount of tension when we pull it over than when it was at equilibrium. But at the moment we let go, we're not pushing it back to the left or throwing it to the right. We're just releasing it. So its initial velocity is 0. So let's copy this information and try to use that to find our values of C. Paste. Let's see if we can drag all of that. All right, I think that's got it. So if we substitute these values in, let's start with x. We needed our x prime as well. So remember, the derivative of this, we get negative root 20 over 3 c1 times sine of root 20 over 3 t. If we take the derivative of that, we get root 20 over 3 c2 cosine root 20 over 3t. We take the derivative of that, we get minus 3 sine t plus c4 cosine t. So if we substitute our original, every place we have a sine of 0 is 0. So when we substitute 0 in, that's gone. When we substitute 0 into that one's gone. So we get c1 cosine of 0. Cosine of 0 is 1. Oops. Plus, gotta go away. So substitute 0 in, cosine of 0 is 1, so we get c1. Sine of 0 is 0, so that's gone. Cosine of 0 is 1, so we have a plus c3. Sine of 0 is 0, so that's gone. And when we plug the for x, that equals 0. So that gives us an equation of c1 and c3. If we substitute a 0 into our derivative, sine of 0 is 0, so that term is gone. Cosine of 0 is 1, so we get root 20 over 3 c2. Sine of 0 is 0, so that's gone. Cosine of 0, so we get c4. Cosine of 0 is 1, so 1 times c4 is c4. So then if we do the same thing with the other one, let's go ahead and substitute in y first, and then we'll come back and get its derivative. So if we substitute a 0 into this function, and I'm getting ahead of myself. So in our derivative, when we plug the 0 into x prime, the answer to that should be 0. There. Okay, so now going back here. So y is 0. put a 0 into this equation. Cosine of 0 is 1, so we end up with minus 3 halves C1. Sine of 0 is 0, so that's gone. Cosine of 0 is 1, so we get 4/3 C3. Sine of 0 is 0, so that's gone. And when we put a 0 in for y, that should be 1. Now, we need y prime. So y prime, if we take the derivative of this one, we have the derivative of cosine is minus sine, so minus and minus is going to make that a plus. 3 halves times the derivative of the inside, that's times C1, and the derivative of cosine is sine. And then when we take the derivative of this, the derivative of sine is cosine. The derivative of the inside is root 20 over 3, so we're going to have a minus 3 halves times root 20 over 3 times C2. When we take the derivative of this, the derivative of cosine is minus sine, so we're going to say minus 4/3 C3 sine. The derivative of this, the derivative of sine is so plus 4/3 C4 cosine. And when we substitute a 0 into there, that term goes away, that term goes away. The derivative, or cosine of 0 is 1, so we have minus 3 halves times the square root of 20 over 3 C2. Cosine of 0 is 1, so plus 4/3 C4. And when we plug a 0 in to that derivative, we should get 0. So that's our 4 equations and 4 unknowns. There's C1 plus C3 equals 0. There's square root of 20 over 3 C2 plus C4 equals 0. There is a minus 3 halves C1 plus 4/3 C3 equals 1. And then there's a minus 3 halves root 20 over 3 C2 plus 4/3 C4 equals 0. Notice these two equations both involve C1 and C3. These both involve C2 and C4. So we could really solve this as two separate systems of equations. We could call it C1 plus C3 is 0, minus 3 halves C1 plus 4/3 C3 is 0. To make these cancel, we can multiply the top equation by 3 halves. 3 halves over here would make a 0, so those cancel. So we're going to get 3 halves plus 4/3. So our common denominator will be 6. So I have 9/6 plus 8/6 C3 equals 0. So that's 17 over 6 times C3 equals 0. And guess what? If we divide both sides by 17 over 6, C3 is 0. If C1 plus C3 equals 0 and C3 is 0, C1 is also 0. So that's going to help whittle down our system here in a minute. Now let's look at our other system. We've got root 20 over 3 C2 plus C4, and we've got minus 3 halves root 20 over 3 C2 plus 4/3 C4. This one, oh, I just noticed a mistake I made. This one is 0. This one is 0. So let's come back to that one. Sorry. This was supposed to be a 1 here, wasn't it? That one's supposed to be a 1, so that would make this 1, which would make this 1. So if we multiply both sides by the reciprocal, C3 is 6 over 17. C1 plus C3 is 0, so C1 C3 equals the opposite of C1, or C1 is the opposite of C3. So that's C1 and C3. Make sure I did that right. So when we added those cancel. Common denominator is 6. So times 3 times 3, that's 9, 6. Times 2 times 2, 8, 6. That's 17 over 6. That's the coefficient of C3. So yeah. So that's C1 and C3. Now if we go back here, what we thought happened with C1 and C3, that's what's going to happen over here most likely. We can multiply the top and the bottom equations by 3/2, so that we have 3 square roots and minus 3 square roots, so those cancel. When we add these together, we're going to have sum C4s equals 0. When we divide both sides by our coefficient, C4 is 0. If we substitute 0 in for C4, if that's 0, then that would have to equal 0, and the only way that can equal 0 is if C2 is 0. So that means our solutions, if we copy x and y, let's copy these over and put the correct coefficients in. So C is negative 16 over 17. C3 is 6 over 17. C2 is 0. C4 is 0. So everywhere we have a C2 and a C4, those are gone. So for x of t, minus 6 over 17 cosine root 20 over 3t. And we have a plus 6 over 17 cosine t. So that's our position function for x. For y, C1 gets multiplied times this. So when we do negative 3/2 times negative 6 over 17, the 2's and the 6 reduce. Negative times negative is positive. So we get 9 over 17. That's the coefficient of cosine root 20 over 3t. And for this one, 6 over 17 gets multiplied times 4/3. So 3 goes into 6. So that gives us 8 over 17. So that's our position y. So we can graph those, and we can look to see what the position of x looks like over time and what the position of y looks like over time. Okay, real quickly, let's go in and take a look. So I've gone into MathCAD. I paused the video so you didn't have to watch all of this, but I went into MathCAD and I wrote these functions that we just came up with, the x and the y. And remember, that's not a horizontal and a vertical. Both of those are horizontal displacements. So the one on the left, this is the block, the first block that was connected to the spring that was connected to the wall. So when we first pull the second block over and let it go, the first block is going to start going a little bit to the left, and then it's going to get pushed, or I'm sorry, it's going to start going to the right, and then it's going to get pushed to the left. And then it's going to start coming back towards equilibrium, and it's going to get right past equilibrium, and then it's going to go back a little while before it goes way to the right. So notice we have, look at these peaks here, and these peaks here. So we have some oscillation we have a general sine or cosine wave that's going like this. We also have some intermediate oscillation as well. Remember, we talked about the normal or the natural angular frequency. So we have two. We have this angular frequency, then of this block going completely to the farthest to the right and the farthest to the left it can go. But we also have this intermediate oscillation as well. We have this little oscillation here and oscillation here, oscillation here, oscillation there. So those have two different natural frequencies. We look at the block that's to the right. Remember, we pulled it to the right 1 unit and we let it go. So it's going to get pulled back to the left and it's going to go past its equilibrium some, and then it's going to get pushed back past equilibrium, and then it's going to go back and forth. So it's not just one steady sine or cosine wave. And the reason I turned it this way, normally you would put time this direction and y this direction, time and x, but so this shows us our position of the blocks relative to where they are. So when the block is to the right, our point is to the right. When our block is to the left, our point is to the left. To the right, to the left, to the right, to the left, right, left. And everywhere we're on this line, that's when our block is at equilibrium. Equilibrium. So I just wanted to see you to have an opportunity to see this application of these systems where instead of just having one single block, we have two blocks. So we end up with a system of differential equations instead of just one single differential equation.